let's see what the integration property looks like in the frequency domain. Okay, so here's we have f of tau d tau, and we want to see what this operation looks like in the frequency domain. Applying our definition of Laplace transform right here, L for this integral expression, we substitute the definition of the Laplace transform from 0 to infinity, e to the minus st dt. Alright? Now we define some variables, and we're going to do integration by parts. So we can take this integral expression, call it y, take e to the minus st dt and call it dx. Integration by parts is defined as follows. Y dx is equal to x times y minus x dy. So notice here on the left side of this equation is our expression for y dx. Now we need to figure out what x and figure out what dy is. So here's dy is just f of t dt. And then x equals minus e to the minus st divided by s. So when I take the derivative of this, I get this expression here. Now, going back where we want to get the integral of this integration operation, substituting this expression with the integration by parts right here, and then substituting, we get the following. So we take this x and y, so our x is this, our y is this, that's what this expression here is, and then x is this, so that's associated here and here, and then our dy is given by this, here and here. But we look at this expression here in the second term of this equation, and we recognize that's f of s. Alright, and this expression here goes to 0, because when you substitute infinity right here, alright, this goes to 0. And we're left with this expression here, f of s divided by s. So what this says is that where f of t is here, we get the corresponding f of s, and then when you operate on this integral, we multiply it by 1 over s. So instead of doing this integral, if we know what the Laplace transform of f of t here, or f of tau in this case, it says then the Laplace transform of f of s, and if I want to integrate it, then I multiply by 1 over s. Okay, here's an example using a ramp. Okay, show that the Laplace transform of r of t, t times the unit, so just to show that the Laplace transform is defined from 0 to infinity, is given by 1 over s squared. Alright, so here we have the Laplace transform of f of t. Substitute f of t for this expression, get this, and now we have u of tau times d tau, which is our ramp. Okay, taking that expression and then multiplying it by 1 over s, because that's the integral. Alright, but we note that the Laplace transform of a unit step is just 1 over s. Okay, so this first s is due to this integral property, and now we need to find the Laplace transform of u of t. Okay, but the Laplace transform of this unit function is just 1 over s. So this is due to the integral, and this is due to as a result of the Laplace transform for a step. And therefore, the integration of a ramp is 1 over the Laplace transform of a ramp is 1 over s squared, and we use the integration property to show that. Okay. Next, we'll look at the differentiation property, and was governed by this. Laplace transform of df dt. By definition, it goes from 0 to infinity, df dt times e to the minus st dt. That's just the definition of this Laplace transform operator. Again, we're going to do the integration by parts, where dx is defined as follows, and y is defined as e to the minus st. So again, as a reminder, this is what we'd have for integration of parts. Y associated with his, and then dx is associated with this expression here. dy then is taking the derivative of this, yields minus s e to the minus st dt, and x, integration of this, the dt's cancel out, and therefore dx is just f of t. Now taking the Laplace transform and doing the substitution and applying this integration by parts, substituting our expressions here, here, and here, we get the results for the substitution with this integration by parts. Okay? Again, we recognize this expression in the second term of this equation as f of s. And this expression goes to 0, or the initial condition for this f of t. Okay? So when you substitute the upper limit of infinity, it goes to 0, and then the lower limit right here is just the initial condition for that function. And then simplifying, if the initial condition is 0, then doing a differentiation operation on f of t is just simply multiplying by s. So the d divided by dt operation, or our differentiation property, means that this derivative d divided by dt with respect to t is multiplied by s. Okay, so that's our differentiation property. Here's an example with differentiation. Okay, we want to show that Laplace transform of a cosine now is associated, but we already figured that out for a sine. Okay, notice we in a earlier example it's s squared plus beta squared. This time we have an s in the numerator. So we note that taking the cosine of beta t, since we already know this, if we take the derivative of sine beta t with respect to t, then we note that sine of beta t has a Laplace transform of beta over s squared plus beta squared. Okay, and we know that d dt has an operation of s. Okay, so there's our s. So we multiply beta, s squared plus beta squared, as a result of this Laplace transform for s, and then we multiply by s minus the initial condition associated with s when t is 0. Alright, so but this is just 0, this expression here. Alright, and that leaves the betas cancel, and that leaves s in the numerator, resulting in this expression. Alright, so that's our differentiation property.